Alrighty, so today we are going to be tackling a problem of capacitors in circuits. And for those of you following along at home, this is problem number 39 in chapter 16 on page 562 in your book. Alrighty, so essentially we have this diagram of circuits up here, and they're nice enough to even draw it out for you in the book. And we're looking for the equivalent capacitance of the capacitors, the charge on each capacitor, and the potential difference across each capacitor. So equivalent capacitance, charge across each capacitor, and our potential difference, that's the delta V across each capacitor as well. So in order to get into this, the first step is to find the capacitance equivalence. And in order to do that, we need to know our two rules about combining capacitors. Because all of these capacitors will be combined and could be represented by what's called an equivalent capacitor, which is just one capacitor that has the exact same capacitance. So when we are in series, the net capacitance is equal to, the net capacitance will be equal to 1 over the sum of the reciprocal of the capacitors, plus 1 over C1, 1 over C2, plus 1 over C3, dot, dot, dot. And that could keep going. In parallel. And this doesn't mean that they are mathematically parallel, it just means that, like right here, it just means that the current could go across either branch. There are two separate branches. And so the capacitance net here is equal to the sum of the capacitors, rather than the reciprocal of the sum of the reciprocals, which gets you a completely different relationship. Dot, dot, dot. So we first want to simplify parts of this that we can, and then we're going to combine it all together. And so right here, we can turn this combination of capacitors, which are in parallel, into a net capacitance. And we can find a little capacitor that is equivalent to these two capacitors. So the net capacitance across this parallel branch segment here is going to be equal to, and I'll draw it out here again for you. So here's capacitor, that one, and here's our other capacitor. And so this one is 2 microfarads, this one is 6 microfarads. And so the equivalent capacitance C net is just the sum of that, and that's going to be 8 microfarads. And so essentially what we can do is we can replace this segment here with one capacitor of 8 microfarads. And so we're going to imagine that that's going to happen. We're going to imagine that this is being replaced by a capacitor that is of 8 microfarad capacitance, because they are equivalent. This segment here, it's as if there were in fact just one capacitor of 8 microfarads of capacitance. And so now we see that we actually have 3 8 microfarad capacitors in series. And so to find the net capacitance of the entire circuit, which is just these 3 in series, we are going to use this equation up here. And so we're going to do 1 over 8 microfarads for this capacitor, plus 1 over 8 microfarads for this capacitor, which we already said was equivalent to 8 microfarads, and 1 more. And so doing a little algebra, that will get you 8/3 of a microfarad. And so with 8/3 of a microfarad, that is our equivalent capacitance. And so that covers that segment right there. And so now we are going to find the potential difference, that's the voltage across each capacitor. And so the rule that you need to know for that one is that capacitors in series have the same charge across each equivalent capacitor in series, but they do not have the same voltage. So they are going to split up the voltage of the battery. And they're going to split it up proportionately to their capacitance. And so once they split it up proportionately to their capacitance, since each of these segments is 8 microfarads, they're each going to evenly split up this 9 volt across each of the three capacitors. And so I'm going to write that this is 8 microfarads up here just so we can remind ourselves about that, since we said that these two capacitors could essentially be combined to become one 8 microfarad capacitor. So since each of these three are going to split up 9 volts evenly, that gets us 9 volts divided by 3 gets us 3 volts on each capacitor. 3 volts on each capacitor. And so that gives us 3 volts here, 3 volts here, and 3 volts total for this branch of 2 parallel capacitors. And so the rule that we are going to use to solve that is, it turns out that on parallel capacitors, the voltage across each capacitor, the potential difference from, say, this plus to that minus and this plus to that minus, they're the same. So to go from here to here is going to be 3 volts, and to go from here to here, this plus to that minus, is also going to be 3 volts. So because it was divided evenly among 3 8 microfarad capacitors, because they're all the same capacitance, and because these parallel capacitors are in fact in parallel, so their voltage is the same across them, that is why we are able to very nicely and neatly say that every capacitor will have 3 voltage across it. The charge is a little bit of a different story. Now, we said earlier that the voltage is distributed evenly among the 3 capacitors, but the charge is going to be the same among the 3 capacitors, and it's going to be the same as awesome. And it's going to be the same as the total charge that is moved around. So what we are going to do to solve for the net charge is we are going to figure out the total amount of charge that was moved, and then we're going to see how it gets distributed amongst each of them. So our total charge, Q total, is going to be equal to, our Q total is going to be equal to the capacitance times our net voltage of the battery. And so we know this rule. This is our foundational formula for capacitors. And so this is going to be equal to 8 thirds microfarads times 9 volts. And that's going to give us 24 microcoulombs. And so since in total 24 microcoulombs of charge was transferred, that means that on this capacitor right here, this plus or minus, this side's going to become plus, and this side's going to become minus once it's connected to the battery, that there's going to be plus 24 microcoulombs of charge here, and minus 24 microcoulombs of charge here. And in series, that will be the same trend across all of these 8 microfarad equivalent capacitors. So for C1 and C4, for Q1 we're going to call is the charge on capacitor 1. Q1 and Q4 is going to be equal to the total charge that was moved by the battery. That we know because these capacitors are in series, and therefore our rule is that the charge will be the same across it and equal to the total. And then this parallel branch here will have a total of 24 microcoulombs of charge. But that total is going to be split up amongst a 6 microfarad and a 2 microfarad. And since the amount of charge we have, our Q, is directly proportional to our capacitance, because capacitance is a measure of, well, how well you can store charge, then we know that the amount of charge on C2 versus the amount of charge on capacitor 3 must be proportional to that 6/2 aspect. So we can calculate that since C2 over C3 is equal to the charge on 2 over the charge on 3. And since C2 divided by C3 is 6 divided by 2 is 3, we know that this is equal to 3. And the microfarad units will cancel out, so this charge is in fact actually just equal to 3. And we know that they are going to sum up to total 24 microcoulombs. So for those of you who are doing the mental math in your head, you will get that Q2 plus Q3, the charge on capacitor 2 plus the charge on capacitor 3, must be a total of 24 microcoulombs. And since Q2 now equals 3Q3, then we know that by substitution 4Q3 is equal to 24 microcoulombs. 4Q3 came from substituting 3Q3 into Q2. 3Q3 plus 1Q3 is 4Q3. 4Q3 equals 24 microcoulombs. Therefore, on Q3, we must have 6 microcoulombs. And then on Q2, we must have a remainder of 18 microcoulombs. And there we have it. So that is the charge on Q3. That is the charge on Q2. It's a little off to the side, but that's okay. So let's box in that part of our answer. Let's box in our part of our answer here for Q1 and Q4. And these values should make sense. This is our net capacitance. And so these charge values should make some sense because Q1 is 8 microfarads, is on an 8 microfarad capacitor. Q4 is on an 8 microfarad capacitor, so they should both have the same charge. And since they're 8 microfarads, we expect them to be able to store more charge than, say, a 2 microfarad. And in fact, they store 4 times as much. And no coincidence here that it is 4 times as good at storing charge. It has 4 times as much capacitance. So I hope this made capacitance and circuits a little bit easier to understand, and I will see you next time.